Okay, last video for this example, I promise. So in part one, we derived equations for the total linear momentum in the vertical direction and the horizontal direction, and that gave us a couple sets of equations that we then combined together using some slick tricks with some trick identities, and we got this equation right here from all of our momentum stuff. Now, in this equation, we still have two unknowns, V2 and V1, that show up in a couple places on here. And that's close, but we need another equation. And since this is an elastic collision, we're going to remember that total kinetic energy is conserved. Now, even though this is in two dimensions, remember, kinetic energy is a scalar value, so it doesn't really have direction. So we don't do cosines and sines in this direction with our kinetic energies. It's really just the velocities themselves. So I took the kinetic energy of our first proton before the collision and the kinetic energy of our second proton, which is just zero because it was stationary. And this total kinetic energy before the collision should equal the total of the two kinetic energies after the collision. So I used that Ke is 1/2 mv squared, and I got myself down to this equation right here. And now I have those two equations and those two unknowns that I can now solve as simultaneous equations. So what is it that I want to do? I want to do another substitution here. Okay. This equation right here is already solved for V1 initial. So I'm going to take it right in and put it up right in that equation. And after I write that equation, here is what I get. V2 squared equals V1 squared plus V1 squared plus V2 squared minus 2 V1 initial V1 cosine theta. Woo. If we simplify though, look, V2 squareds, we can subtract those away. And we get that 0 is equal to 2v1 squared when we combine like terms minus 2v1 initial v1 cosine theta. Real simple. This actually isn't as bad as it might look. And then we have a factor of 2 in both of these. So let's go ahead and just reduce that out. And we get this v1 squared minus v1 not v1 cosine theta. And what I'm noticing here is that I actually do have a quadratic in terms of V1. And while I could plug this into the quadratic formula, I kind of noticed this form is that I could just do a quick factor V1 and factor out of V1 from both of those, and I get V1 minus V1 naught cosine theta. And my two answers should be these two cases, one where V1 equals 0, or the case where V1 minus V1 naught cosine theta is equal to 0. And this one over here to the left doesn't really make any sense. This would say that our first ball hits into, our first proton hits into the second proton and stops dead. But that does not happen in this case, right? That does absolutely not happen. This definitely deflects off at an angle. So this is going to be our true situation. And we can now solve directly for V1 by substituting our values for our initial velocity and our 37-degree angle. So let's do that real quick. All right. And that means that V1 is equal to V1 naught cosine theta. And I know you probably want to punch me in the nose right now because we went through all of that just to find this tiny little equation. But there are some considerations that we'll talk about in the end here. So our initial velocity is 3.50 times 10 to the 5th meters per second. And we're going to multiply by that by the cosine of 37 degrees. and we get a velocity v1 of 2.80 times 10 to the fifth meters per second. So we have one of our unknown values. Let's find our next unknown value. Let's go for v2 now. And to do that, I am going to use my energy equation right up here. All right. That's one of the simpler ones that I have that have V1, V2, and V1 not in it. So I'm going to go straight for that. And in this case, I can kind of rearrange it to say that V2 is equal to the root of V1 naught squared minus V1 squared. All right. And if I plug in my values for V1 naught and V1, then I get a value for V2 of 2.11 times 10 to the fifth meters per second. And I am so close to the end of this answer. Okay, so I have the magnitudes of the velocities for my two protons, m1 and m2. And now I just need the direction psi. All right, and to do that, I'm going to go all the way back to the vertical momentum equation that we wrote that looks like this. We said that V2 sine psi was equal to V1 sine theta. And if we want to solve for psi, then we just have to rearrange this a little bit. All right, so we'll divide both sides by V2. And then we're going to take the inverse sine. So psi is equal to the inverse sine of V1 sine angle theta over V2. And we get an angle of 53 degrees. And we're done. We found all of our givens. We found all of our unknowns. I know this is really, really long, and when it came down to it, the equations seemed really, really simple. Why couldn't we just jump to those conclusions? But some of the things that I want you to consider before you just jump in and maybe start using an equation like this is the initial conditions of our problem. I want you to remember that we had one of our objects stationary at the very beginning, and when it collided, right, we only had the momentum from the first one to begin with. The other thing that we had to really consider is that these two things had the same mass whenever they collided, and all of those things led us to the equations that we see up here. Don't just jump to conclusions and assume that you can use any one of the equations through the middle of this problem, because we really had to get each one of them through derivation. So consider those things when you're doing your homework, and good luck. It's going to be long, but just stick with it. I'm sure there'll be plenty of times where you have to crumple up your paper, but you'll be cool. Trust me. All right. See you on Monday.